Hello, everybody, to today's webinar. It's a pleasure to introduce today's speaker, Žiga Virk from the University of Ljubljana. So Žiga has this great intuition on how to use persistent homology and other stuff from computational topology in geometry. Today he's going to talk about detecting geodesic circles with selective Rips complexes. Please, Žiga, go ahead.
Okay, thank you. Thanks, Nisa, for building up expectations. And I'd like to thank the committee for organizing this nice online seminar. So today I'm going to be talking about detecting geodesic circles with selective Rips complexes. So here's the main idea. We are all mostly familiar with persistent homology. And we know that persistent homology measures, at small scales, it measures topology of the space. So essentially, if you have a nice space, you call homology. While at larger scales, persistent homology encodes geometry of a space in some way. So today I'm going to be talking about this interplay between algebraic elements generated by persistent homology and geometry. So first I will start by reviewing some of the known results, and then in the second part I will focus on selective Rips complexes, where essentially we do the converse in the sense that we decide that we want persistent homology to detect special geodesic features. These are geodesic circles. And in order to detect as many as them, we can adjust the construction of Rips complexes to detect these things. So instead of starting with persistent homology and trying to explain that in terms of geometry, we will pick a geometric feature and try to set up a persistent homology computation so that we will be able to detect those things. All right. So let's start with the introduction and setting. As I already mentioned, we'll be talking about persistent homology. We will always be using at the beginning Rips complexes. So starting with our space X, for the sake of simplicity, you can just think of a surface. So we'll have uncountably many points, but they will be they will form a nice space. We will construct Rips filtration and then eventually compute persistent homology. So as we mentioned, persistent homology encodes the geometry in a way, but how does it work? I mean, what information it actually encodes? That is, the exploration of that question is the main topic of my research. Actually, it's been the main topic for a while. So in our specific setting today, we will focus on geodesic spaces. So that means that for each pair of points, there exists a path from X to Y of this length. These paths will be called geodesics, just for the sake of simplicity. And an example of such a space is the circle with a geodesic metric. So if you take a topological circle and metrize it in a way so that the shortest distance along the circle actually realizes distances, we get what we call a geodesic circle. And so that's the expression we have for a specific metric on a circle. But then again, we also use this term of geodesic circle to express certain subsets of geodesic spaces. For example, if we are on a sphere, the equator is a geodesic circle. Or if you have something more complicated, like something like this, here we would have several geodesic circles. One would be this, another would be here. And then, well, depending on the local geometry, we would typically have one geodesic circle going around here, one coming inside this hole, and then one going around here. Now, our assumption is that, well, our expectation is that these are significant geometric features, and throughout this lecture we will try to explain how to detect these geodesic circles with persistent homology. So as a part of a review of the previous work, we actually have 3 ways of detecting such circles in a space. You can actually do that with 1-dimensional, 2-dimensional, or 3-dimensional homology, and each of these approaches actually has a different flavor to it. The first one is a topological detection with 1-dimensional persistent homology. So the idea here is the following. If we construct the Rips filtration of a geodesic space, and I'll be skipping assumptions like locally contractible or things like that. As I said, just think of a compact surface. So when we're dealing with 1-dimensional homology of Rips complexes, in any coefficients, so the coefficients will not matter for my analysis here at all. It turns out that these maps are surjective. So the bonding maps on the Rips 1-dimensional homology of Rips complexes are surjective. And consequently, we can classify the kernel of these maps. And it turns out that the kernel is generated by loops of length less than 3. Now, what that actually means is that as we're increasing our scale parameter of the Rips filtration, we are killing off, well, that's a violent word, more and more loops. And the criterion by which these loops get eliminated is their length. Equivalently, you could also use other criteria, but we're not going to go into that direction here. So it turns out from this, it actually follows directly that the 1-dimensional persistent homology, just homology of Rips complexes, can be easily computed by just taking 1-dimensional homology of our space X and modeling out all loops that are of length less than 3R, or in specific case, that means that you just mod out the shortest element, shortest base of the 1-dimensional homology, or, well, I should say differently, those elements of the shortest base that are of length less than 3R. And an additional feature here is that the geodesic, the geometric feature that actually induces this shortest base, so actually the loops representing shortest base are all geodesic circles. And they can be actually reconstructed from critical simplices. To provide a simple example, suppose we have a torus. It's a bit thinner on the front end. And if we want to compute its, well, if we compute its 1-dimensional persistent homology, the result is the following. We get 2 bars or 2 points on the persistence diagram. They both start at 0. And end at 1/3 of the length of the circle. We get something like this. So that's nice. So just from these diagrams, you get the length of the shortest homology base. But actually, if we take a critical simplex, inducing such elimination in persistent homology, we can actually reconstruct the whole homology base. So something like this is done here. We took a torus, which is kind of, it's not thinner at the front end. We computed 1-dimensional persistent homology, just took the critical triangle, connected the vertices at the critical triangle, and we got a nice representation of the shortest homology base. So the computations here don't contain just the lengths of the generators. You can actually locate those geometric features here. All right. So this is a topological detection because these loops are obviously topologically significant, forming a shortest homology base of H1. The second type of detection is combinatorial, and for that one, we use the result of Michal Adamaszek and Henry Adams. Henry is around here somewhere. So they proved a really nice result. For me, this is like a hop type result in persistent homology. So they proved that, okay, if you take a geodesic circle, so just a circle with a geodesic distance, the circumference is 1. Then for small scales, you get your Rips complex is homotopy equivalent to S1. That's a known result. But then at 1/3, magic happens. So one-dimensional homology elements here get eliminated by equilateral triangles, this sort. And you can stack these triangles in a funny way so that they form a 3-dimensional sphere. And then later they start forming 5-dimensional sphere, and you get all odd-dimensional spheres. So the moral of this fact is that low-dimensional geometric features, let's say, so this is a 1-dimensional circle, they can generate higher-dimensional algebraic objects in, let's say, persistence through the combinatorics of Rips complex. So we can actually use this thing to devise, in a way, a combinatorial detection of a 3-dimensional persistent homology. So the idea is the following. If we have a geodesic circle, and it also turns out that we want to require a neighborhood like this, if it has sufficiently large, I want to say hyperbolic, but it's not, doesn't really depend on the curvature. It could be positively curved. You want to have a neighborhood that you can squeeze in, and while squeezing these things toward the central arc, you want all distances to be decreasing. I like to call this kind of transformation, deformation contraction, because it's contracting things. Hausmann called it crushing. So there's at least there are at least 2 terms to describe it. All right, so if you have a sufficiently large neighborhood like that, and then besides that, you need to satisfy certain technical conditions that I would rather skip at this point, then it turns out that when the scale parameter of the Rips complex passes 1/3 of the circumference of this circle, of this geodesic circle, the Rips complex of this geodesic circle itself attains the homotopy type of a 3-dimensional sphere, and that 3-dimensional sphere actually survives in persistent homology of the whole space. So in particular, 1-dimensional geometric thing, a loop, generates a 3-dimensional persistent homology element through the combinatorics of the Rips complex. This can be proved by Meyer-Vietoris exact sequence. The proof is not hard. The hardest thing is actually to set up the right definition. An approach like that works for other subspaces as well. So this specific approach, this combinatorial detection, does not restrict only to geodesic spaces or loops. Then there's also the third approach, and that's actually geometric detection with 2-dimensional persistent homology. And in that detection technique, we actually use the way in which a loop is embedded into a space. So here's a setting. Suppose A is a geodesic circle as before, and again, we need sufficiently large neighborhood of this sort. Then, well, what we also assume is that A is our loop here, our geodesic circle of interest. we assume it's homologous to a combination of shorter loops. Now, this is no big deal because if A is not homologous to a combination of shorter loops, we can easily detect it with one-dimensional persistent homology. So this is actually, as far as practice goes, it's not a big deal anyway. So if conditions like that are satisfied, then it turns out that A induces a two-dimensional persistent homology generator. How does it do that? We'll explore that in the next picture, and actually throughout the rest of this talk, we will mostly be interested in expanding this specific result to as wide class of geodesic circles as possible. So what we will want to do is we will want to say that, well, whatever the size of a neighborhood of this sort we have, we want to be able to detect a geodesic circle A. All right, example. So this is result of Henry and Michal, just for quick recall. Our space of interest will be torus here. It has two bottlenecks, A and B, A and C. These are both geodesic circles. And below we have a barcode. So let's go through this barcode. Now for small scales R, we know that the homology, the persistent homology, persistent homology at that point, let's put it this way, it reconstructs the homology of our space. So that's what we get, zero-dimensional elements, two one-dimensional elements, and one two-dimensional element. And then, as we pass 1/3 of the shortest geodesic circle, this loop here gets eliminated by persistent homology. However, if we have a sufficiently large neighborhood of the sort we described earlier, the Rips complex of this subset of geodesic circle A itself attains the homotopy type of a three-dimensional sphere. And that thing actually survives as a non-trivial three-sphere in the whole persistent homology. So this is the three-sphere arising here. Okay, that's the first transition I want to talk about. The second transition is at 1/3 of the circumference of C. So at that point, given sufficiently nice neighborhood, which this should appear to be, again, we get a three-dimensional element in persistent homology. So that's the combinatorial way with which you can detect C, but there's also a two-dimensional thing popping out. How does that appear? So recall that by this time, by C divided by 3, A is contractible. Let me put something like a lead here over A. The lead actually has the homotopy type of a three-sphere, but for this specific argument, we don't care about that. So once we pass 1/3 of the circumference of C, we also get a lead here. And as a result, we get a two-dimensional enclosure here. So that's a two-dimensional element in persistent homology that detects C, and it appears here. All right. So, and then the same thing happens for geodesic circle B. One-dimensional class dies out, and at the same time, the three-dimensional class appears. So actually, just to recall, we have three ways of detecting geodesics. These lines are actually topological detections, detecting the shortest homology base. Three-dimensional bars are actually combinatorial constructions arising from the combinatorics of Rips complex. And two-dimensional bars appear actually from the geometry of our space. So because we have a locally shortest geodesic circle, which is homologous to something shorter, and this homology bringing C to A actually encloses two-dimensional thing. Let me show you another calculation actually. So for example, if you take a sphere and you cut out the top of the sphere and induce geodesic distance on it, the upper part, this loop will become a geodesic circle now, even though it's not a geodesic circle in the sphere. And running through persistent homology, we see that at 1/3 of the circumference, well, no one-dimensional bar should die at that part, but although we have here some one-dimensional bars, but these can all be increased because they actually appear because the computations are done on a finite collection of points, not on the whole uncountable collection. So as I was saying, at 1/3 of the circumference, a three-dimensional bar appears, and a two-dimensional bar appears. So trust me, I checked, I zoomed in this picture, there is one green pixel here, so it is a three-dimensional thing. And if you check through that result of Michal and Henry, this is about the size that's expected for that three-dimensional bar. So that, first of all, it's hard to compute because it uses higher dimensional simplices than two-dimensional bar. Second of all, it's very short. So it looks much more promising if you try detecting loops using two-dimensional bars because they're easier to compute and apparently they appear to be longer. And then later we also get some clutter. I think these are all extensions of ephemeral summands corresponding to large circles in the sphere, but I haven't been able to prove that yet. But the lesson here is that, well, computing this persistent homology, we can actually interpret everything that happens in terms of geometry. All right, so is there any question at this point? So this is kind of a review of the state of the art up until, let's say, last year. All right, so this looks nice. So it means that whenever we have, well, that often when we have bars in persistent homology, we can interpret the critical elements giving rise to those bars as geodesic circles. The problem, of course, is that the conditions I described, if one checks the technical requirements, they require sufficiently large nice neighborhoods, so they may not always appear there. So what I want to do in this second part is, as I already mentioned, I want to switch the game. I don't want to compute the persistent homology first and then interpret it. I want to choose a geodesic circle and say, well, if it's locally shortest, if it's kind of a bottleneck, I want to tweak the computation of persistent homology so that I will be able to detect that loop. Okay. So we'll start by building geometric intuition that will lead towards this kind of result. So first, let's check the geometry of two-dimensional persistent homology elements arising this way. So if this is a part of our surface, let's say, and this is our geodesic loop, then the two-dimensional homology element that we described, that we saw on previous slide, consists of two parts. One is this blue part, which is essentially, in this specific case, a null homology of the geodesic circle A. But in general, it could be a way in which this circle is homologous to shorter loops. And the second part is this thing. I would call it a lid. So it's a lid you put on. You could fill it in only once your scale parameter increases over 1/3 of the circumference of A. And putting this lid on, you obtain two-dimensional thing. In specific, this is what, if I draw a lid like this, actually the combinatorial description would be something like this with triangles. There's typically one triangle that's almost equilateral that reaches all the way across the loop. And the issue with the size of the neighborhood that I was mentioning earlier is the following. Okay, I can put a lid somewhere like here, but if the rest of the surface is too close to this lid, everything, this whole generator of this sort might be trivial because it's just too small. So for example, if I take a sphere, it's an example that we had on the previous slide, and I cut it off real close to the equator, so close that the distance between the South Pole to this parallel has to be less than 1/3 of the circumference of this thing. Then by the time I will be putting this lid over it, so that's 1/3 of the circumference, the whole Rips complex of this space will be a cone over South Pole, meaning it will be contractible and there's no way for me to detect a loop like that. So things don't work with as they stand. Previous results don't apply. So let's start to think about how to get around this problem. The trick is to use thin tetrahedra. So how do we get to them? So here's my setting now. This is my geodesic loop A. It is a bottleneck loop, meaning it's locally shortest in some small neighborhood, N. All right, and the idea is the following. I don't want the cone formation of the previous slide to happen. So what I actually want is, if a triple of points circumvents A, so let's say, for example, we have points like this, so that when we draw the shortest path, these are geodesics, from one to another, we actually go around. Oh, that's a terrible picture. Then I don't want the tetrahedron to be really thick. So I don't want the tetrahedron containing all these points to go somewhere really far outside this neighborhood. This is something I don't want to happen, because then I won't be able to detect this kind of loop with persistent homology. So the requirement is I want to have usual triangles because I want to keep the time at which the lids appear. We could actually modify that as well, but it doesn't help us. But I want to have thin tetrahedra. So usual triangles, just like with Rips complexes, but I want to have thin tetrahedra. And here's the way how to do it. We define selective Rips complexes. So maybe I should just display the whole finish and then discuss it. So what I will have are two scales. R1 is the smaller scale. It tells me that, and in this setting R1, 2, it means that the selective Rips complex with these parameters up to dimension 2, that means up to 2 skeleton, is the same as Rips complex. However, for higher dimensional simplices, I want them to be R2 thin. What does that mean? that means that if I take any simplex in X, I want to be able to cluster the vertices into 3 sets, each of which is of diameter at most, well, less than R2. For our purposes, diameter is just the easiest way of to measure the size of a set. We could also choose small as a closing circle and get a kind of selective check complex. Excuse me? All right. So in specific case, as long as you're looking just at the tetrahedra, this definition means that one of the sides has to be of length less than R2. So tetrahedra have to be R2 thin, but, well, so in 2 dimensions they can be as wide as they want, but in 1 dimension they have to be R2 thin. Okay, and the funny thing is that once you define selective Rips complex, you can define a local winding number inside your really thin neighborhood. So still, as before, this is my geodesic circle A with a very thin neighborhood where the geodesic circle itself is the shortest non-contractible loop. So just for technical reasons, I will draw 2 nested neighborhoods. N1 is the smaller neighborhood, and N, just capital N, the larger neighborhood. All right, so let's define the local winding number. If we have a triple of points in this large neighborhood, then the winding number, the local winding number, is defined as K if and only if a filling of T is homotopic to A to K in this neighborhood. A few things. What's a filling? If you have a triple of points and you connect them pairwise by a geodesic, geodesics may not be unique, but if you connect them by geodesic, you get a circle, you get a loop, and that is a filling. It's a loop in this neighborhood. That's why we need geodesic convexity here, so that the loop stays in the neighborhood. And also there is a bound on the depth, but it's a technicality. Let's not worry about it now. So anyway, once we have a triple of points, which is not of too large diameter, we can fill them, obtain a loop, and determine its winding number. Now, as it stands here, K seems to be just some integer, but in fact, we can easily prove that under right specific circumstances, K can be either 0, 1, or -1. So if you just have 3 points, you connect them. I mean, it's kind of obvious. You cannot go twice around this neighborhood. So the idea is that points which are kind of close and on one side of the neighborhood, these should have winding number 0, while points that actually that form almost an equilateral triangle going all the way around, they have a winding number 1 or -1. All right. Then there's a lemma that comes into play here. It looks terrible, but I just want to draw the parameters of what they mean. The lemma itself is actually quite natural. So what it says is that if I choose N1 like this, and the width of N1 will be this T, then I can bound the diameter of triples here. So this will be the diameter. So that whenever I have a triple circumventing within this neighborhood, meaning that the local winding number is non-trivial, it actually has to lie inside N1. One is missing here, inside the smaller neighborhood. Right? So that means that if I'm not allowed to stretch those points too much, and I want them still to include, to kind of circumvent the whole thing, well, I can bound that diameter so that these kind of points stay here. If you think of it, it's a very natural thing, and it's not hard to prove. It's just a technical thing that one needs later. Okay. Now with this lemma in mind, we can actually define a local winding number of, well, let's be ambitious, of a homology class. So we have a two-dimensional homology class in S Rips complex. Yeah, I should probably put more coefficients here. This is S Rips of R2 and mu n. It means that the tetrahedra have to be mu n thin. So this is this bound on diameter. Okay, so how do you define local winding number? You take two-dimensional homology class. For each triangle that appears in a, well, let's say, to put it formally, you take a two-chain, and for each triangle appearing in that two-chain, you check whether the vertices lie in N. If the vertices lie in N, you use this definition. If at least one of the vertices is outside, you define the winding number just to be 0. So the winding number is actually in this way defined for all triples of diameter at most this, either for the ones that are outside N or not completely in N, but it will only be trivial for the ones in N. And the thing is that defining a local winding number like that is a well-defined thing. It's a good invariant. So it is an invariant of a homology class. So here's how we prove it. It's a really easy proof that can be drawn. It suffices to show that actually the winding number of any chain to obtain as a boundary is 0. Okay. So the boundary of a tetrahedron that consists of 4 triangles, and for each of them we take a filling, that's a loop, and the winding numbers should add to 0. So assume we have a non-trivial face. So assume we have a face of our tetrahedron that has a non-trivial bounding number. Now, by the lemma before, that face has to lie in N1, in the smaller neighborhood. Okay, so let's term consisting of 3 points. These 3 points are here. And then, if in the definition of the Rips complex we choose mu n, so that the measure telling us how thin the tetrahedra are, if that is less than the distance between, well, less than this distance, then also the 4th point of our simplex has to lie within N somewhere. Okay? And then once you have that, you just use geodesic convexity and see that, well, the winding numbers have to add up to 0, because what you're actually doing, well, we're taking a tetrahedron, we're taking its boundary, and we're filling the boundary of the boundary. So because twice the boundary is 0, everything works out. At this point, this argument seems trivial because, well, twice the boundary is 0, but actually, unless you have a nice neighborhood like that, it actually doesn't work. it's not a homology invariant, which can be deduced from the example we had before, where if you cut out a sphere too close at the equator, you cannot detect that circle using usual Rips complexes. All right. So with this in mind, we can prove that detection of actually a fairly large class of geodesic circles works well. So this is probably the only point where I will write down all requirements. If X is geodesic, semi-local is simply connected and locally compact, and our loop is a geodesic circle, a bottleneck loop, meaning that it's the shortest in some neighborhood of itself. If this is not the case, then it's easy to see that there's no way to detect such a loop. And third, it has arbitrarily small geodesically convex neighborhood. Then the construction above works. So the construction is that, well, whenever you have a loop like this, you construct a homology element like this. You compute its local winding number at n, and looking at this slit, this circle is actually triangulated. You need to discretize everything, of course, because you're doing triangulations in computing homology in Rips complexes. But the lit can be decomposed in this way, where the only triangle of non-trivial winding number is this central triangle. All other triangles have winding number 0. And the triangles forming this blue part can be made arbitrarily small anyway, so there's no way for them to cause any harm. So once you set up this whole machinery, the proof is actually fairly simple. You just write down this thing, winding number is non-trivial, and that's it.
Question.
Sure.
What are the parameters that you use for your S-Rips complex?
So let's go back. I just put this thing. There are two parameters that one can think of. One of them is you will be getting a two-dimensional bar arising from this circle. And the larger this neighborhood is, the longer that bar will be. The length of that bar will actually depend on the circumference here, and actually a few more things. Actually, what's the quickest way when the boundary becomes contractible in Rips complex? So the wider this neighborhood, the longer the bar. And the parameter of Epps Rips complex will be this distance, actually. So the longer you want your bar to be, the smaller parameter for Rips complexes you will need to have. So there's not just one specific parameter, of course. When you compute, maybe you don't want to make your tetrahedra ridiculously thin, so there's kind of a balance. But so if you're asking for the upper bound for the parameter of S-Rips would be this distance.
So the distance between those two neighborhoods is like the third parameter of your S-Rips complex.
Yes,
right?
That's right.
Yeah. Okay.
Yeah, and you can make n1 arbitrarily small. Your bar will be smaller, but yeah, this is theoretically how far it can go.
Okay.
Thanks. That's a good question.
Thank you very much.
So this is parameter. This is R2 of S-Rips. All right, where were we? All right, this thing.
Is there a way to estimate that parameter beforehand? Like, I don't know.
Well, you need to know how large that neighborhood is. Otherwise, there's no way to know.
Oh, okay. Thank you.
Yeah. Yeah, I don't think there's any way to go around that. I mean, even if you just want to reconstruct homology of a manifold, you need to know something about its curvature. So also, if you have, let me draw here. If you just have a geodesic circle, and let's say in the neighborhood there's nothing shorter, it could still be a part of a cylinder. And in this case, you still will not get anything. So you need to have, first of all, neighborhood of this sort, and second of all, some bound on the size of this neighborhood.
Okay, thank you very much. Yeah.
Sure. Thanks for the question. All right. So this local winding number is very handy proving these things, but it actually has another nice property, meaning that with it we can actually localize the geometric feature generating this two-dimensional class. So when you're doing computations with persistent homology, turns out that when you're dealing with Rips complexes and you have, let's say, points in general position, there are two choices for the critical simplex that will construct a two-dimensional class. Why is that? Well, the two-dimensional class will form at certain radius, and once you reach that radius, an edge will appear, and typically that edge will have to be face of two triangles. So those two triangles, either of them can appear as a critical triangle. For example, I tested that with Ripser, so it depends on the case which one you get. But if you take the one that is not thin, meaning the one that's almost equilateral, and there will always be one like that, you can actually do the same thing that happened in the first animation before. Just take 3 points there, just connect them by geodesic in a space, and that will give you your geodesic circle. So for a cutoff sphere, this is something of that sort. This demonstrates what the critical triangle is. At least for two-dimensional persistent homology of geodesic spaces, I think that's a better representation of a homology class. I mean, drawing a two-dimensional homology class, it can be done. It's challenging, but if the whole thing actually arises from a one-dimensional geometric feature, then this might be a better representation of it. All right, so that's the positive side. The negative side, well, it's not such an issue, is that there is some clutter appearing. So why is that so? Just to demonstrate the issue, let's decrease the dimension a bit. Let's say we're building selective Rips complexes and I want our triangles to be thin. Not tetrahedra, we're going one dimension lower. So let's compare what happens in the case of Rips complex and S-Rips complex. We'll be considering what happens when this edge appears. So in Rips complex, when edge appears, the whole triangle gets filled up. But in S-Rips, if you require your triangles to be thin, once this edge will appear, the triangle will not fill up. So you will get a lot of lower dimensional clutter. It's not going to be very persistent, at least at the beginning, or that's what you hope. But then if you do computations with it, this is what happens. It grows. So this animation is actually showing what's happening if we are decreasing this factor. We started with Rips complex, and then this factor was decreasing. This factor tells us how thin the tetrahedra have to be. And we see we get a lot issues there. Well, the good thing is that there's kind of a workaround around this. It's not such a big deal. So up to now, we only talked about rips, selective rips complexes at a certain scale. And when we were doing persistent homology with it, we said, well, our thickness will be just some coefficient of our scale R. And that's what we did in this case. This is an example of a sphere where we cut off the top part. The cutoff was low enough so that the Rips complex would not detect the upper geodesic circle, but selective Rips does. So we're very happy about this thing. We're kind of worried about this thing, but the trick we can use is that let's not take this to be a linear function. We can change this to a function of R that is R at the beginning, which would mean that for small scales, we will have just the usual tetrahedra. We want those small holes to be filling up. And that at larger scales, and again, which are those scales depends on the size of your loop, you start getting thin triangles. So if you take a function like this, we get rid of this clutter, and we still keep the detection properties here. So the function was constructed so that we get past this issue first, and only at, let's say, this point, we start making thinner tetrahedra. Okay, so at cutoff like this, things work. If you start cutting off spheres higher, we get pictures like this. So once we reach certain heights, Rips complex will start detecting that geodesic loop on top, but selective Rips will still have a more prominent feature representing that thing. And the same works here. So both of them detect them once the height is high enough, once the neighborhood becomes large enough, but still for S Rips, the difference is more significant. All right, so up to this point, just have a few more minutes. The next slide is actually the last mathematical slide. Up to now, we were just talking about these neighborhoods and how they appear, and there is a fairly natural environment where these neighborhoods are natural. This is the space of hyperbolic surfaces. So here is just an overview of results of a preprint we're just finishing. So what happens? These results, the right part, are the results I was talking about up to now. So earlier we had some three-dimensional footprint detection, meaning that some three-dimensional spheres were generated using some fairly complicated condition here actually. And we mentioned that as long as we have a convex neighborhood, geodesic circle, and a bottleneck loop, so if a loop is has these properties, then a two-dimensional thing appears. Now it turns out that if we're in hyperbolic manifolds, all loops are bottleneck loops. That's actually a fairly known thing. It's not a big deal at all. And that convex geodesic charts appear as soon as we have geodesic charts with some width. So geodesic chart of a loop means that while one component goes along the loop and the other component goes perpendicular to the loop, and then you just use the usual exponential map. So a very specific example where such things occur, if you have a unique systole, if you have a unique shortest non-contractible loop in your space, you can always detect it this way. And parameter actually depends on the spectral gap between the shortest and second shortest non-contractible loops. So much for two-dimensional things. In three-dimensional footprint detection, it turns out that the structure of hyperbolic manifold actually allows us to deduce this complicated machinery just from the geodesic chart. So as long as you have geodesic charts of some width, you get three-dimensional bar in persistent homology. Okay, so that's it at this point. I would like to thank my student, Matthias Schuffer. He did some of these animations using Ripser, and then also his own code, ripser.jl in Julia. That's all I had to say, so thanks for your attention, and I'm looking forward to questions.
So thanks very much, Žiga, for this really nice talk. Very interesting. So do we have any questions?
Žiga, I wanted to ask a question. So, this three-dimensional homology signature of a loop doesn't generalize so well to identifying like two spheres embedded in, because it'd have to be embedded in isometrically, right, which is much more restricted for two spheres. But the wall construction, where you have this loop and then you're building this wall, say with the S-thin Rips complex, right? That seems like that might work as well to identify higher dimensional features. Is that the case? Have you thought about that, or this winding number? Is there an analog of that?
Yeah, that's a guess I would try to make. So that's I would say a natural further line of research. Yeah. So I don't have any results in that direction, but this would be a hope. Yeah.
Very cool. Thank you.
Good question. Thanks.
Thanks, Henry. Any more questions for Žiga? I have a not very sophisticated question. In your notation for the selective Rips complex, you have a 2. What does that 2 stand for?
It tells about the dimension where you start having thin simplices.
Okay, so do you have versions where there's something else than 2 written there?
Okay, here we go. Yeah. So this, in definition, it tells us this 2 is this 2, actually. And that kind of controls dimension. So actually, we have a more general definition where we have a sequence of R's, and the simplices are getting thinner and thinner. And I think at this point that changing these numbers gives you certain local minima of a configuration space. So there is some idea about what to do with different numbers, not just 2. 2 is defined. I mean, here we did 2 because we're talking about loops, and there you want to have thin tetrahedra. But in general, yeah, I think that it's a reasonable line of thought to try to think about other dimensions here and see how what you can get out of them.
Thanks. Any more questions?
I have a question, maybe. So if I understand correctly, the Rips complexes you use, they're from, in principle, X just some sort of manifold or something?
Yes.
But what happens if I now use a triangulation of a manifold? So I plug in not a manifold per se, but actually something that might come from data. So I have some discrete set in Rn and some distance there. Does this then also work under certain? Well, is there a way to translate it? Maybe my question.
Yes, so the underlying idea here is that when translating to applicative setting, that one can use stability of persistent homology. So if I get two-dimensional bar here for computation using all uncountably many points and perfect geodesic distance, then if I take a nice sample and generate geodesic distance on that sample, persistent homology should be kind of similar. Now again, how fine of a sample that should be, but that's actually what happens here. So this is actually a real an example computed on Ripster. So my student took a dense enough sample on the sphere, generated geodesic distance, and we got precisely what we wanted. So of course, by stability, there can be some small deviations here, depending on your density and how well you approximate that metric. But in general, yes, the idea is to try to think of this continuous analysis of persistence diagrams first, and then to use that understanding as an approximation to what happens in practice when you, as you said, you have some specific triangulation on finitely many points. I hope I answered the question.
Yes, thanks.
Thanks. Any more questions for Žiga? Well, if not, Žiga, thanks very much for this really nice talk. And thank you everybody for joining us today. So see you next time at the webinar. Invited to the next session. So bye-bye.